This is the first lesson in Unit 13-14. This is going to cover boxes A and B. So first we want to talk about the material in box A here and just refresh ourselves on what we mean by the composition of functions. And to sort of motivate this, let's just consider some examples here. We're given two functions. We got f at x, which is x plus 2, and g at x equals x squared. And the question we're asking is, how can we combine these two functions to form a new function? And then once we've done that, how do we find the derivative of this new function? So one thing you might say is, well, let's take our let's form our new function h at x by taking f at x and multiplying it by g at x, which would give us something like x plus 2 times x squared. If we then wanted to find the derivative, h prime at x, what would we use to find that derivative? Well, we would use the product rule that we talked about last unit. So I'll just say use product rule. Or we could imagine forming our new function by dividing these two functions. We're doing f at x over g at x. Okay. Then if we wanted to find our derivative, we could, well, obviously we would use the quotient rule that we talked about last unit as well. Use quotient rule. Now there's another way of combining these functions that you learned about in advanced functions, doing the composition of these two functions. And the goal of this unit is to get you to be able to take the derivative of functions that are made up of two simpler functions that are composed together. This is where all of this is heading. But so let's just refresh ourselves on what we mean by composition here. So if we want to write h at x is the composition of our function f and g, remember the notation that we used? We said we used f composed with g of x like that. So the little circle means that we're doing the composition. Okay? So this is the composition of f and g. And what did this mean in practice? It means that we took our function f, and wherever we had an x in that one function f of x, we would substitute our other function g of x. So this is kind of like evaluating f at x at g at x, was another way of writing it. So in our specific example here, if we look at our functions f at x was x squared plus 2. So here's f at x is x, and instead of the x, I've just left the brackets for what we're going to sub in, something plus 2. What are we going to sub in there? Well, we're going to sub in our function g at x. G at x was x squared. So we just stick an x squared in there, and that would be our new function, x squared plus 2. And of course, we could do this the other way as well. We could have a different function, a new h at x, then instead we do the composition in the other order. This is g, the composition of g and f. Okay? And the thing to keep in mind is that this gives us a different answer than doing the composition of f and g. So if we want to do g of f at x, we are taking our outer function, g at x, and into it we are subbing our inner function, f at x. So what does that get us this time? Let's see, g at x was x squared, so we're going to have something squared, and into this we are going to sub f at x. What was f at x? It was x plus 2, so we sub x plus 2 into it, and then if we wanted to, we could simplify this by expanding x squared plus 4x plus 4. Okay? So that was composition. All right. So let's just take a look at two quick little examples here. So here's the first one. Two more functions. F at x equals the square root of x squared plus 49. G at x is x to the power of 4. We want to find, let's do f of g at x, and over here we'll do g of f at x. Okay. So for our first one here, we'll just remind ourselves that f at x is our outer function, so we're going to take f at x and we're going to evaluate it by subbing in our function g at x. So what do we get when we do this composition here, applying it to these two functions? Nick?
Root bracket x, root bracket x to the power of 4.
Okay, yeah. So root bracket whatever we have in there for x, and what we're putting in there for x is x to the power of 4. Okay, and then we got the 49 in there as well. Can we simplify this at all, Nick?
Yeah.
What are we going to do?
Just take away the square in the bracket.
Can you take away the square in the bracket?
Root is square.
But are we squaring everything in there?
Sorry?
Are we squaring everything that's underneath that root sign?
Yeah. I think 49 squared.
Mm-hmm. We're adding these two things together. There's a plus sign in between them, right? So we can take the square root of both of them, but we can't take the square root of, well, we can take the square root of both of them, add them together, but we don't get something that works out nicely. So, do you get what I'm saying? If we had x to the power of 4 times 49, yeah, we could take the square root of both of those things and get x squared times 7. Okay? That plus sign in there means that we can't take the square root of both of those. Okay? So we can't simplify it that way. The only thing we can do is apply our exponent laws to simplify this first term here. So we're going to have the square root of all of this stuff, and we multiply those. We get x to the power of 8 plus 49. And that is our new function. Okay. So same thing, let's do it in the opposite order here. We'll do the composition of g and f. So that's going to be g as our sort of our outer function here, and we're going to sub into it our function f at x. What are we going to do when we do this composition here?
It's just bracket root square plus 49 bracket to the power of 4.
Right. So we've got our big thing here, something to the power of 4. We sub in x squared plus 49 into there. Can this be simplified? How?
You just the root. Simplify.
Okay, how do we
So
simplify?
I would put it in exponent form.
Good plan. What is it going to be in exponent form?
4 over 2.
Okay. So I'm just going to write out explicitly what we're doing here, right? We're changing that square root to a 1/2. And then again, we're applying the exponent laws. So what's our final answer going to be?
X squared 49
To the power of 2, exactly. Just applying the exponent laws, 4 times 1/2 gives us 2. And if we wanted to, we could expand that out by multiplying, but that's too hard for me to do right now, so I'm just going to leave it. Here's what we want to be able to do in this unit, okay, is we want to do sort of the opposite to what we've been doing here. We want to take some function that looks really, really complicated, and instead of doing the composition, we want to do like the decomposition. We want to think of this function here as two functions that have been composed together. Okay? And that's why we're doing all of this rehash of composition of functions. So a good thing to be able to do is be able to take a function like this and write it as two functions that have been composed together. Okay? Now, how can we do this for this one? The first thing I would do is I would start by rewriting h at x into a little simpler terms. I've got a cube root here in the bottom, which gives me an exponent of 1/3. And because it's down in the denominator, I know it's going to be a negative exponent. So I'm going to rewrite h at x as this x squared plus 7, which is under the root all to the power of negative 1/3. Okay. Now, can we come up with two functions that we might have done the composition of that would have given us this expression here? Richard.
X to the power of negative 1/3 and x squared plus 1.
Yeah. Okay. So we'll call one of these f at x. We'll call one of these g at x. Okay. So, and I'll just say if f at x equals x to the negative 1/3 and g at x equals x squared plus 7, then h at x is, now, is it the composition of f and g, or is it the composition of g and f? Which way does it go? Yeah. Okay, or f at g at x, because we're putting g at x here in here where f is, and so on and so on. Okay? So that's really what we want to be able to do in this unit. Okay? The other skill that we need for 1314 is we need to be able to factor, basically common factor, some complicated expressions. Now, obviously, number one here is not a complicated thing to common factor. I'm just putting it up here for, well, just to remind us of what factoring is. So we've got an expression here, x to the power of 4 plus 10x to the power of 3 plus 3x to the power of 2. If I said common factor that, what are you going to factor out of each of those three terms? Just x, yeah, x squared. So why do we factor out x squared? What is important about x squared? It's common in each of the terms. And how do we know that it's the biggest thing that is common to each of these terms? What does this x squared represent if we compare x to the fourth, x to the cubed, x cubed, and x squared? It is the, that's not the leading coefficient.
Oh, sorry.
1 would be the leading coefficient. It's the coefficient on the highest power of x.
Yes.
It's the smallest, it's the lowest power of x. Okay? Yeah. And I know you just look at it, okay? But this is me putting into words what you think when you look at it. You think, okay, that's the lowest power of x, so I'm going to factor it out. And to show you something even more obvious, how do I do this? I write the x squared out front, and then I take each of these terms, and I divide them by the x squared. Okay? This is something your grade 9 teacher probably showed you when you were first looking at factoring. Okay? And then inside the brackets here, I'm applying my exponent laws. Right? So I'm subtracting those exponents. X squared plus 10x plus 3. Okay? This is what I want to do when I'm factoring in this unit. So let's take a look at this second example here. Similar to the first one, but now instead of positive exponents, I have negative exponents. What am I going to factor out from each of these terms here? Yeah, x to the negative 4, because again, that is the lowest power of x. Okay? So just to write it out in gory detail, if I've got 3x to the negative 2, divided by x to the negative 4, plus 10 x to the negative 3 divided by x to the negative 4, plus x to the negative 4, x to the negative 4, right? I'm still applying those exponent laws, but I'm subtracting a negative exponent, so I'm adding exponents. So I'll get x to the negative 4 times 3x squared plus 10x plus 1. Okay. I show this because I often mess up on questions like this, where I have to subtract negatives instead of adding them. I don't know why. All right. You also have to be able to deal with fractional exponents when we're doing this. Okay? And again, this is nothing new. You've been working on this, but you're going to get a lot more practice in this unit. So what am I going to be able to factor out of these three terms? And this one is nice because they all have the same denominator. So I'm going to factor out x to the 2/3. Okay? Is there anything else I can factor out? 2, because it's a common factor, right? So, hey, thanks. Yeah, I switched from x to y. Thanks. We were talking about lowest power of x, and then somehow I switched to lowest power of y. Okay? So we can factor out 2y to the 2/3. Okay? Now, I have three terms in this original expression here. That means I need to have three terms inside this bracket. Okay? Sounds obvious. This is another common mistake people make. Okay? So we're going to have three terms in here. What is the first term going to be? 1. Okay? And this is the one that often disappears, the constant terms. People think, okay, I've already dealt with my 2x to the 2/3. Okay? Anyhow, we'll keep going here. Factor out the 2, I'll have a 3. And then I'll have y to the, let's see, 5/3 minus 2/3 is 3/3, which is just 1. And 4, 8/3 minus 2/3 is 6/3, which is just 2. So y squared. Okay. Last type here. Okay. Then I'll give myself a little bit more room. Now our common factors in our terms are binomials. So we want to factor out, again, the lowest power of each binomial. So let's see. What is common? Let's see, what's common here? Well, we've got a y plus 3, and we've got a y minus 4. So we're definitely going to factor out something that has y plus 3 and something that has y minus 4. What power of y plus 3 are we going to factor out? Well, we look for the lowest power. Let's see, we've got a -4 and a -3, so we'll factor out a -4. And then when we look at y minus 4, we have the option of factoring out 4 or 3. We factor out the lowest power. Okay? So that's what we're going to take out. Now, this tends to be long, so I'm going to move this down a little bit here. Okay? To give myself a little bit more room. Okay? So this is what I'm factoring out. Give myself square brackets here. How many terms do I have in my original expression? Well, I have one plus sign right through there, so I'm going to have two terms. If I factor out these things here from this first term, one thing I'm going to be left with is this 2 that's out in front. So I'm just going to put that 2 there at the beginning. Okay? And from my second term here, I've got a 3 that I'm going to be left with. Okay? Those coefficients often get forgotten. Okay? So I like dealing with them first. So then, let's see. I factor out y plus 3 to the -4. Okay, so that takes care of all of those in this term. So I'm just going to be left with y minus 4 term. So y minus 4, let's see, 4 minus 3. So y minus 4 to the power of 1, just y minus 4. Then in my second term, let's see, y plus 3 to the -4, y plus 3 to the -3. I'm going to be left with a y plus 3 here. And what is the exponent going to be? Well, let's see. -3 minus -4. gives me a 1, so just y plus 3. And y minus 4, both to the power of 3. Those guys take care of themselves. So my factoring there is done. Now I can simplify this thing that I have in the square brackets. Y plus 3 to the negative 4 stays the same. Y minus 4 to the 3 stays the same. And inside those square brackets, I can expand and simplify. 2y minus 8, 3y plus 9, again in square brackets, and simplify again by collecting my like terms. So I'm going to have 2y plus 3y is 5y, and then negative 8 plus 9 is just positive 1. And there we go. We've got it fully factored. Okay? So this one simplifies considerably when you get it into factored form. Okay? So those are the basic kinds of factoring that you're going to need to do as we work our way through Unit 14, 13, 14. Questions?